So this question, we have 13 minutes. And a question like this should take about that much time. So you have two blocks connected by a string of negligible mass. So the string is negligible mass, massless pulleys, negligible friction. Mass 2 is greater than M1. That would make sense from the sizes. They are released from rest. So we would expect then that if this is released from rest, this whole system is going to accelerate. And that's the key thing here. Yes, this is going to drop. This is going to go up. The whole system is accelerating. And everywhere inside this system is experiencing the same acceleration in that direction. Remember, when we have pulleys, we could consider redrawing them as being redirected into a straight line. And of course, we know everywhere inside this string, the force is the same. But this whole system is accelerating to the right. So they'll share the acceleration. So now we want to know the two blocks. We want to draw free body diagrams and label the forces. We must have labels as well. So draw free body diagrams, label the forces. Draw relative lengths to reflect the negative magnitudes, the relative magnitudes. So first thing we know is that M2 is the biggest mass, and that's going to be the biggest force. So we could put FG2. And we know the weight of 1 is less, so let's make it some number smaller. So we're clearly indicating in this case that the mass of block 1 is less than the mass of block 2, resulting in lower forces. Now, when we draw, if we draw each of these blocks independently, here's FG2, but there's also tension, force of tension. And FG1, there is a force of tension. So we know we must draw forces of tension in the opposite direction. The question is, how do they relate to each other in size? How they relate to each other in size is, if you are a molecule anywhere in that string, you are not accelerating relative to the others. You're accelerating together. So that means that everywhere inside there, the forces are the same. So the two tensions are the same in magnitude, equal and opposite direction. Again, if we take one of these molecules inside here like this one and blow it up, well, it's being pulled in that direction and pulled in that direction, equal and opposite. It's not accelerating relative to these guys. So then when we go to draw that force of tension, have them like so. So then what we can see then is that when we write out our equations, these two will cancel each other because they're in opposite directions. Next, we're being asked to drive the magnitude of acceleration of block 2. We can only have M1, M2, G, and A, the acceleration. This is all about forces, and that, my friends, is Newton's second law. And that is F net is the sum of the forces. F net is MA, and this is the mass of the system. Then the question is, what are the different forces? Well, if we stretch this out in a straight line, say this is the positive direction and this is the minus direction, we have FG2. We have FT minus FT because it's in the negative direction. We've got positive FT in this direction. And then we have FG1, like so. So our sum of the forces are, which is the other direction, so it's minus FG1. So the sum of those forces then is FG2 minus FT plus FT minus FG1. Just wrote them all down. Now these two, of course, are going to drop out because they're equal and opposite. And we have mass of the system times the acceleration is FG2. And let me just do a substitution there. FG2 is M2G minus M1G. And we are looking for an expression for A, so we divide both sides by mass of the system. And I'll do some factoring while I'm at it. factor out a G, M2 minus M1 all over mass of the system. Well, what is the mass of the system? The system consists of those two masses, M1 and M2. So G is M2 minus M1 all over M2 plus M1. And that is my expression that we are looking for. Now, some of you left it unsimplified and, like back here and so forth. When they say find an expression, derive the magnitude of the acceleration A, you should have an expression that's A equals. It should also be clear which version you're looking for. So now when we go to the part C, we're looking at this. Now what's happening is we still have no friction. It's a frictionless situation, and block 3 of M3 is added. There's no friction. It doesn't tell us how massive M3 is compared to M2 and M1, but it may not matter. And so we want to know now what happens to the acceleration. We had this system where it's M1 and M2. Now we are going to just add another block in there. Block 3. Well, if we do our free body diagrams, so for mass 2, we have the weight, FG2, and we have the tension. And we have mass 3, which experiences the tension, its weight, FG3, force normal 3, and the force of tension. And then we have block 1, which is FG1 and FT. I'm going to highlight those that matter because these two rotate. Rotating these forces so that they're aligned correctly, we get FT, FG1. Here we have FG2 and FT. Again, our positive direction and our negative direction. And then on 3, we have this FT and FT. Assigning the positives and negatives, well, FG2 is positive, this FT is negative, this FT is positive, this FT is negative, this FT is positive, and this is negative. So the net force is the sum of the forces, and the net force is MA, mass of the system A. And the sum of the forces, then, starting from the right, is FG2 minus FT plus FT minus FT plus FT minus FG1. So the mass of the system is M1 plus M2 plus M3 times the acceleration. These two drop out, and we are left with FG2, and we'll do the substitution for MG. M2G minus M1G. Solving for A, we get M2G. We'll factor that out like we did on the previous page. So we've got G M2 minus M1 all over M1 plus M2 plus M3. So this looks virtually identical. The numerator is the same. The denominator is similar, except there's an additional mass. And increasing the mass in the denominator causes the whole term to reduce. So the acceleration will be less because the same net force, which is FG2 minus FG1, is now accelerating a greater mass. And that's this question.